Okay, let's take a little bit deeper dive into this idea of MIMD. Specifically, the area that we're going to focus on today is something referred to as tightly coupled. Now, whenever it comes to multiple processing units, all being able to communicate with each other in order to do some sort of a shared application, we need to have some way that they can communicate with each other. And typically what we've got is some sort of an interconnection network. Now, in the area of, in the name of defining this thing tightly coupled, what you're doing is simply defining exactly what this interconnection network is made of. And in the case of tightly coupled, it's a shared memory. We're passing information back and forth, not through messages, but actually through values that are in reserved portions of memory that all the processing units can see. And by the way, right up front, I need to apologize for this pen. I have been battling for basically a couple of hours to try and get this video done because the pen keeps failing on me. There's new batteries, new driver, everything. So I apologize right up front for any sort of goofy handwriting and so forth due to the pen. Now, the other thing that we're gonna even more tightly focus our discussion here by talking about these processing units here. Whenever it comes to the the, um, the configuration we're talking about today, these guys are all going to be symmetric, and they're going to be symmetric in a number of ways. But because they're all symmetric, in other words, their capabilities are all identical, this is referred to as a symmetric multi, let's see, I'll try and get this pen to work again. Symmetric multiprocessor, otherwise known as an SMP system. Now, SMP systems have been around for quite some time. Usually, early on, they were a single circuit board. So you notice that we have the two sockets here, and each socket has its own access to memory. Now, there was some sort of memory controller that allowed us to pass information back and forth between those devices. They do share sections of memory, but each one has its own local or high-speed access to its own memory. Still, passing information back and forth between a memory. Now, if we go to something more like our Raspberry Pis, where we've got some sort of a common GPU, and then we have multiple CPUs. So we have these different cores, core 0, 1, 2, and 3. But now the shared memory has been brought much closer. It is now close to us in the form of a shared L3 cache. Now each one of these cores has its own L1 and L2 cache. Those L1 and L2 caches serve a very important purpose. They allow us to access our own code, our own data quickly without having to take up the shared memory. The interaction between the cores and the memory, that can be a bottleneck. So we want to stay out of it as much as possible. But the other thing is if I modify some sort of a value in the shared memory, I need to be able to alert the other processors that might be using that value. So let's talk a little bit about symmetric multiprocessors and what makes them symmetric. Well, first of all, one of the most important things that makes them symmetric is the fact that each one of them is physically separate, but they have the same basic characteristics, the same capability, the same capacity, same functionality. So you're not talking about different levels of performance, you're not talking about different instruction sets, you're not talking about different sizes of file registers and so forth. These are all the same the same basic capacity. So as I said before, it can be on a single die or maybe on a single PCB that share items across the system bus. But another thing that makes them symmetric is not only do they share the same memory and I/O, but the access time in order to store or read something is about the same for each processor. Yes, we have the memory hierarchy, and so the speed of accessing an L1 cache is going to be different than the speed of accessing a system memory. But each one of them has the same approximate time to access system memory, the same approximate time to access their own L2 caches. For all intents and purposes, they should be performing at exactly the same speed. Now, there is going to be some sort of, and we're going to talk briefly about the operating system. There is going to be some sort of a shared operating system. It may be distributed. It may just be, on one of the devices. But each one of them, in order to operate as a multiprocessor system, there has to be support from the operating system. In addition, as I said earlier, each one has its own high-speed memory, usually in the form of an L3 or an L2 or just an L1 cache. Now, it is not. This is one of the things that we haven't really talked about Amdahl's law. Amdahl's law basically says there is an upper limit to the performance that we can achieve by throwing multiple processors at a problem. So for example, let's say that we have two processors that are on our system. Well, two processors, that would imply to us that we could operate twice as fast. Amdahl's law says that that's actually an upper limit. We are choked, of course, by the fact that we are now going to take our RAM may be a little bit slower because of the fact that now this RAM is being shared across multiple devices. And we have this thing called cache coherence, which is going to be what we're going to talk about for the last part of the lecture. The ability to make sure that if I modify something in my cache that is shared across all other caches, I need to make sure that everybody's cache is up to date. That overhead takes some time. And there's also the overhead of our own process. Each process, there are some things that can be done in parallel, but there are some things that have to be done in a single thread. That's going to take away from the fact that our performance is not proportional to the number of processors. In addition, there are some applications, and believe it or not, there are still some older consumer applications that are still out there that weren't written to support symmetric multiprocessors. Typically, the operating system, whenever it encounters one of these, the operating system is going to assign that process to a single core. Performance is not going to be improved at all. All right? But what does happen if we do have a lot of these these single instruction, single data stream applications? If I have multiple applications that can be run across multiple cores independently, we can at least get a little bit of an improvement in performance in the form of multitasking. So, one of the things that, and in fact, there's a couple of things that are really important whenever it comes to going to a symmetric multiprocessor system. One is that we do get a performance improvement, right? I mean, this idea of being able to do things in parallel, having multiple threads executed at the same time, that's going to give you a performance improvement. So we do get a performance improvement even if we have multiple applications that need to be run at the same time that are all meant to be run on a non-SMP machine. One of the things that is also important is note that I did say that the symmetric multiprocessor systems, each one of those processors has the same capabilities. So if we do have some sort of a failure of a single core, that core, as long as the operating system can detect it and kind of cut it out of the list of cores that are available for our processes, we have pretty good reliability. We've lost a little bit of performance by losing a core, but the system is still up and running until we can get some sort of a replacement in place. Incremental growth, well, I always hesitate to include incremental growth in this list of advantages, because when you look at a cluster is really easy to grow incrementally. I get a new machine available to me, I plug it in, and I'm ready to go. Incremental growth, whenever it comes to one of these systems, is not quite as obvious. It's best whenever it comes to one of these systems where you have multiple sockets on a single circuit board. Two may not be the case, but you could have bought this system and only populated the one socket, and whenever you had enough money later on, populate a second socket. Or if you've got one that has many more sockets, you could grow incrementally from there. So as long as the operating system, once again, can detect the appearance of newer cores, yes, you do have incremental growth, but it's not nearly as flexible as a cluster, being able to plug new machines into a network. Scaling, that's more along the lines of whenever I'm selling these devices or whenever I'm purchasing these devices. Basically, that means, if we go back to this processor board up here, like I said, I could buy the board and just have a single core plugged in, still use the system, then add additional cores as I get more money. So that gives us the ability to scale in terms of purchasing. Now, one of the things that's really important to an advantage of an SMP system over, say, a cluster is that it truly looks like just a single desktop that we're working on. So as far as the user is concerned, we don't really notice the fact that we're getting an or how we're getting an improvement in performance. I mean, picture your Raspberry Pis. Turns out that what we've been doing whenever we were doing the bootloader type code was just running on a single core. Still looks like a single system, right? But whenever you turned on your Raspbian or whenever you installed your Raspbian operating system, multiple cores appeared and the operating system was able to define which one of those cores a particular task got assigned to. Now, we are going to talk a little bit later about the physical organization of a tightly coupled system. But as far as the overall organization of a tightly coupled multiprocessor or SMP system, is that each core really is an independent unit, its own control unit, its own ALU, its own cache, its own private main memory, and that we have an interconnection network, but this interconnection network is done through a shared memory. Once again, I'll show you configurations later on that show how this is accomplished at the PCB level. And as we've said before, any of the communication takes place through a shared memory in a common data area. So there is a portion of memory that is set aside to pass variables back and forth. And what we'll see later when we start talking about the different configurations, we'll see that there is the ability to provide access to the memory to the individual processors or the individual cores at the same time.